Hello, business community. Now, we want to apply artificial intelligence for a simple model concerning calculating the customer lifetime value. In the last video, I showed you how to do this in a non-subscription model when your customer disengage over time. But now that having understood how to calculate the probability of a customer that if he remains actively engaged, now we can attach some monetary value to this process. So more or less, we're going to repeat the last Jupyter lab. And now we have the monetary value within our equations, within our model. And we say, what is the monetary value associated with future purchase events? And so the result will be the estimated customer lifetime value. We follow the same recipe as I already showed you in my last video. I will not reiterate everything, so if you want to see it right from the start, please go back and have a look at it where I explain it to you in detail. Now, more or less, we're just loading here from online retail dataset available from the UCI machine learning repository, just to have some default business data. And what we do is, yes, take some time. We have a look at an orders Panda data frame. And what we do is very easily, we say, hey, we have a column called quantity and a column called unit price. So we just calculate the sales amount per customer, and we store it in a new column, sales amount, in our Panda data frame. And then, of course, we create a Spark data frame from our Panda data frame, and we create a temporary view because we want to, of course, explore the capacity of our Spark cluster, have a T2 Spark cluster up and running on this free Databricks Community Edition. And the notebook you see here is provided by Databricks itself. It's a beautiful demonstration object, and I leave you the code to this public notebook from Databricks in the comment to this video. So now we just have to wait till this finish. And as you can see here, invoice number, stock code of the article, the description of the article purchased by a customer, the quantity, how many articles were sold, the invoice date, the unit price, the unique customer ID, the country of origin. And then if we just say, hey, create our sales amount column, we just add the sales amount. This is easy. We create a Spark data frame, we create a temporary view because we want to be able to use SQL commands, and then we explore the dataset. Step 2, explore the dataset. Let's look at the typical daily spend of a customer. We group this at the daily level. Well, you are familiar with this, you know SQL. The Spark job, it is easy. Take some time, but we go on. Come on, Spark. Yeah, it's quite some amount. This is nice. So, the density. The range of daily spend is quite wide, with a few customer purchasing over £70,000 in a single day. 70k. Here we go. Hey, this is almost impossible. I just had it. Okay, forget it. Without much knowing of the underlying business, hard to say if this level is consistent with the expectations. Yes, there are quite a few negative values which are most likely associated with returns. Oh yeah, we have returns. Well, we have to take care about this because, as you can see here, minus £30,000 as a return is quite something. So what we do? Daily sales by customer between 0 and £2,500. Okay, so let's focus on the reasonable spectrum. And then a distribution of daily spend. Yes. Yeah, this looks good. £250 is the peak of our typical Gaussian curve. And then we have a long tail, of course. Yeah. Top customer by frequency. Okay, let's do this. Let's have a look at the first 7. Top customer. This is the customer ID, and this is the frequency calculated. Daily spend for the 3 most frequent customers. Okay, now you have a deep dive to your 3 customers. And as you can see here in the Jupyter Notebook, you can have a really nice visualization. Your top 3 customers. Well, it's not a lot of, but who cares? Okay, step number 3, again, as in the old video, we calculate now the customer metrics. Now, to the 3 that we already know, this is the frequency, the number of dates on which a customer made a purchase subsequent to the date of the customer's first purchase, remember, the age, the unit in days, since a customer's first purchase to the current date, the recency, the age of the customer as defined at the time of their last purchase. Now we have number 4. This is now the 4th value we're interested in, since we have now the monetary evaluation, the average per transaction date spent by a customer during repeat purchases. Now we consider the matrix, identify the last date in the dataset, and define that as today's date for all calculation to derive. We have again the lifetime library, showed you in the last video. It's a Python library which simply import lifetimes. You can see here, I loaded it, so very easy stuff. They saved all the complex mathematical calculation for us. We just use this library, some really nice code. Identical to the one used before, the only difference is that we are instructing the method to use our sales amount field as our measure of monetary value. Well, what a surprise. Here we go. So here again, we have all our customers, I don't know, 20,000, 200,000 customers, the frequency, the recency, the age of the customer, and now new, we have a 4th metric, the monetary value of our customer. And as you can see, they vary quite significantly. So let's examine how we might generate this using Spark, so that when working with larger data sets, we can use in a parallelized manner on a Spark cluster. In the next 2 cells demonstrate we might use this first a SQL statement and then the programmatic SQL API. Now, we do jump to the programmatic SQL API because I do prefer this methodology. Let's run this. And then we can identify again that those 2 methods are equal. Well, of course, SQL is SQL. So what we end up with, all our customers, the frequency, the recency, and the age, and the monetary value. Beautiful. So now that we have this data, yes, we believe the system that the methods are identical. We are using a widget to define the number of days and the holdout period. The holdout period was defined as last time I showed you 90 days. Sounds reasonable. Please adopt it whatever you see fit for your company. Define the end of the calibration period, calculate the required matrices that we have defined, and we display now our Panda data frame with the matrices. Running command, come on, it's not so complicated, it's just a demonstration project. Implement required login and using program. We derive at the following. Oh, again. So we have pure SQL, or you have here what I'm going to use. So here we have again, as I showed you in the last video, the holdout duration, it's 90 days, the monetary value on the holdout. This is clear, and now we just execute here our cell. And then you again can compare that all the methods lead to the same results. We believe this, that Databricks knows how to do the job. Again, duration, holdout, monetary value, yes, there is something. Use range join optimization as a joint condition that can be benefit from a range join optimization. This is nice. So Databricks enables you to learn even. So carefully examine the monetary holdout value calculated by the Lifetimes library. You should notice the values produced are significantly lower than those arrived at the Spark code. Oh, interesting. This is because the Lifetime library, let's do it a little bit bigger, is averaging the individual line items on a given transaction date instead of averaging the transaction date total. The change request has been submitted with the caretakers of the Lifetimes library, but we believe the average of the transaction date totals is the correct value, and we will use that for the remainder of this notebook. Wow, interesting. So they even help other programmers to optimize their libraries. If you'd like to examine how values identical to those currently produced by the Lifetime library can be created using Spark, we recreated the logic using SQL here and provided a summary comparison in the two cells that follow. No, we do not have to verify anything. We just want to understand the method. So here we go. And as always, we just limit our analysis to those customers with repeat purchases. So only customers that come back should be in our time series analysis, otherwise it would be useless. And so finally, we need to consider what to do about the negative daily totals found in our dataset. And we might assume those negatives value represent returns. Ideally, we match returns to the original purchase and adjust the monetary values for the original transaction date. That said, we do not have the information required to consistently do so. Oh, great. Where this causes a daily total to be £1 or lower, we will simply exclude the value from our analysis. Outside of demonstration setting, this would typically be inappropriate. Okay, so you as a company, you know the exact dates, and if you have a return, what it compensates with. Okay, verifying the frequency and now new the monetary value independence. Okay, here we go. Oh, gee. Yes. Before proceeding with our modeling, the gamma-gamma model, named for the two gamma distribution described earlier, that we will employ assumes that the frequency of a customer purchase does not affect the monetary value of those purchases. Okay, it is important that we test this, and we can do so with the calculation of a simple Pearson coefficients against our frequency and monetary value matrix. We'll do this for entire dataset, ignoring the calibration holdout subsets. Okay. While not perfectly independent, the correlation between these two values is pretty low, so we should be able to proceed to our training. Yeah, now finally we can train our model. Yeah, okay, correlation. 0.17, yeah. Not perfectly independent, but okay. Step 5, train the model. Finally. With our metric in place, we can now train the model. Here we go. Finally, we have a little bit of artificial intelligence coming into play. Because up to now, we just have the data preparation, if you want. Estimate the monetary value to be derived from the future transactional events. This is the main goal why we set out to examine this Jupyter Notebook. We want to have the monetary value of future transactional events. The gamma-gamma model. Okay, what is the gamma-gamma model? Explain this to me. The gamma-gamma model of monetary value, February 2008, Peter Fader. Yes, I've heard of him. Okay. Simple stuff, no problem at all. And there's a Python already done for this. We do not have to code this ourselves. Okay, half the fun, but let's use the Python libraries that already did this. The implementation is pretty straightforward using our Lifetimes library we already downloaded and imported. Ah, there's a gamma gamma fitter. I see. With our lifetimes library. We must first determine the best value for our L2 for our Euclidean regularization parameters, like in the old time. And of course, we will return to Hyperopt for the perfect hyperparameter for our model. So we do exactly like in the old notebook, the last notebook I showed you in my last video. We define our search base. We have an evaluation function. We have our mean square error and the root mean square error defined. And then we have a function where we define the evaluation model. Yes, yes, yes. This is gonna take some time. Oops. Distribute your Hyperopt run with Spark trials. Okay, check out best practices for using Spark trials with Hyperopt to distribute your Hyperopt running Apache Spark. Learn more. So nice, so nice. Okay, now configure the Hyperopt setting to distribute to all executors on the workers. We are in the free demonstration. We just have 1 or 2 workers, so would be nice to have a full-fledged Spark cluster, but we do not have because we're operating on the free version, so it takes a little bit longer, no problem at all. We have 100 evaluations. Oh god, this is gonna take some time. So I suppose I will be back with you in 5 minutes of my time and in 1 second of your watch time. And exactly after 6 minutes and 59 seconds, we are back. We have a total of 100 runs, 100 succeeded, 0 failed, 0 cancelled. So what we have logged 100 runs to an experiment in MLFlow. Remember, Hyperopt with Spark trials will automatically track your trials in MLFlow. You can watch here all the different experiments here if you're interested, where you have the date, you have your L2, you have your loss. L2, if I understand, this is .209. This should be it. Let's have a look what we get out. If you have a look at our hyperparameter, you remember we have to have L2. And L2 is now at .003. Wow, this is quite minimal. This is our optimal L2 value identified. Now let's train the final model with our regulation of L2. Yes, yes, yes. Wow, this was fast. Fitted, great. Yeah, if you ask, hey, how big is our model? Just forget to show you the size. We have a data set of 4,372 customers and we have 22,000 transactions going on where we operate our model on. So it doesn't scale linearly up, but just give you an idea about the complexity of this demonstration model we are using. So here we go. Yes, then of course you can evaluate the model. The evaluation is straightforward. Yes, yes, yes. Yeah, let's just run through this without any further explanation. We might also visually inspect how the predicted spend values align with the actual values. This is always a good idea. Check how well your models performed. A simple visual tells you 100 things. Technique employed in the original paper, the gamma gamma model. Yes, let's run this. Let's have a look. Now, as you can see, the orange one is the predicted one and the blue one is the actual data. So yeah, it's not perfect, but this looks quite nice. So it got the trend at least with only 10 bins. Our model looks like it lines up with our actual data pretty nicely. If we expand the bin count, we see that the model under-predicts the occurrence of the lowest value spent while following the remaining structure of the data. Okay, you might say, okay, where is my pin count? Let's go with 30, just for fun. Let's have a look. Yeah, I can see here. The maximum here is there's a mismatch here, and there's a little bit almost a delta here. And then we go on, so you can play around with your bin size. And then, of course, optimize the runtime of your models. Oh yeah, now we can see some significant derivation here in the model. We have to optimize the model further. Maybe take more time or whatsoever. It's already there. Beautiful. I don't have to do this at all. So, and finally, this is our step that you have been waiting for. Let's create a little bit more space here. You want to calculate your customer lifetime value. And here we are after 20 minutes. My goodness. The spend model allows us to calculate the monetary value we may obtain from future purchase event of our customers. We can derive a customer lifetime value for a future period of time. We must first train a lifetime model. This was the content of the last video. We'll use the BGNBD model with an L2 parameter derived in the earlier execution. Last notebook. If you want to have the detail about this, now we just execute this cell. And now we can use these together to calculate the customer lifetime value. And the time period is a 12-month period using a monthly discount rate of 1%. Please fill in your business data as appropriate. The CFO typically defines a discount rate which should be used for these types of calculation. Be sure that the discount rate is expressed as a monthly discount rate. Yeah, annual discount rate, you have to convert it using this formula. Okay, we do believe that they got it right. Let's have a look at this. Panda data frame, customer lifetime input. And here we have it. For our specified customer IDs, we have calculated a customer lifetime value. Wow. Yes. So you can see AI is able to help us. AI is able to train hyperparameters for model. Let the model train, even if it's on a small data set for just some seconds. We got a quite good impression what's going on. As I told you, CLV is a powerful metric used by organizations to plan targeted promotional activity and assess customer equity. Would be very helpful. We have an easy function we could employ in batch, in streaming, and interactive scenarios. So all of this is done as a Spark UDF, for example. And you know we can do this. So let's save our model to a temporary location. So this saved the model. Model is saved. Let's define the custom wrapper for our spend model. Notice that the predict method is fairly simple and returns just a CLV value, exactly what we want per customer. Notice too that it assumes a consistent value for month, and discount rate is provided in the data. We already told about this. Modification to the predict method logic, a new definition for load context is provided. This method is called when an MLFlow model is instantiated. Lifetime artifact, beautiful, beautiful, beautiful. Input series, make CLV prediction, and here we go, spend model customer lifetime value. The model to use to predict the number of future transactions. Here we have our frequency, our recency, our T, our monetary value. We already defined our discount rate and our time. It is 12 months for us. This should be it. Done. And now we save our spend model to MLFlow. MLFlow, yes. Model, do we have model? Conda, MLFlow start run, deploy run. Let's have a look at this. Waiting to run. Yes. Finally logged one run to an experiment on MLFlow. This is done. And as before, we create a function from this model. And you are familiar, define the schema of the values returned by the function. And then define the function based on MLFlow recorded model. And as in the last video, I showed you MLFlow PyFunction Spark UDF. I have a video on Spark UDF if you want to have a little bit of a deep dive. Register the function for use in SQL. Let's do this. And we are done. Our model is now available for use with a programmatic SQL API. create a temp view. Next cell, yeah. Demonstrate functional call on a Spark DataFrame. Yes. So to display the filter column CSV with customer IDs. Come on. Yes, and here we go. This is it. So we have just the function call on a Spark DataFrame, and we get exactly our customer ID, our specific customers, what it was, 2,000 customers, 5,000 customers, I don't remember, and the calculated customer lifetime value for a time period of 12 months, and a discount rate monthly of 1%. This is CLV calculated. Now, wasn't this beautiful? Can also be used with SQL? Well, yes, of course. Let's do this just for a reason of to be consistent with this notebook from Databricks. Okay, aggregate of results, no, based on the first 1,000 rows. Yes, beautifully. Plot option, yeah, whatever you want to do. This is, yeah, 12 months, 0.01, this is it. Yes, and this is it. We are done. Unbelievable. Here we go. We have our, where are we? Here? No. Here we have our customer ID. For each customer, we calculated based on their spending pattern, on their time development, on the amount of money they spent. We calculate the customer lifetime value for each particular customer in this simple program. I say thank you. I hope you enjoyed it. You see, MLFlow by Databricks is a very powerful thing. We have an automatically definition of our most optimized hyperparameter within MLFlow. And I really recommend you learn a little bit about this possibility that an artificial intelligence system, even if it's a simple model like this presented here, can help you to identify your most prominent customers, the customer you should really focus on with your marketing material, with the messages you send out. I hope you enjoyed this video, and if you do, please like, subscribe, and I see you in the next video.